Hi, I'm Zack Hodari, and today I'm presenting joint work with Catherine Lai and Simon King on the perception of learned intonation contour classes. This is for the following paper at the Speech Prosody Conference virtually in Japan. In speech synthesis, we have an issue of missing context. This is because we rely on a limited and static linguistic feature set, where for a given sentence, the inputs will always be the same, no matter the context. This is problematic because prosodic choices are determined by context. For dialogue, this may be related to the turn history, the interlocutor, or the affect of both the speaker and the listener. The physical setting may have an impact, or the pragmatics and external world knowledge may come into play. There are no speech datasets with this kind of broad context annotation. For this reason, we split the problem in half: controllability and appropriateness. In this paper, we approach controllability, where we attempt to produce distinct renditions of isolated sentences. The idea being that for any given sentence, we would then have the ability to produce the appropriate rendition, even if we don't know which is the right one. That would be the task of appropriateness, where the goal would be to predict the most appropriate rendition, relying on context information. In order to model prosody and drive such a controllable system, we have a need for unsupervised learning. While prosodic annotations do exist and are used for speech synthesis, their reliability is often low and they can be expensive to collect. By definition, labeling schemas will not capture all variability in speech, something which unsupervised approaches have the ability to do. For this reason, we've decided to learn a representation to control prosody. We also choose to use a discrete representation, since this provides a more usable domain of control. And this goes hand in hand with our question of interpretability, where it's much easier to ask questions about clusters or classes as opposed to points in an arbitrary space. If we have learned some mechanism of control, the question remains, what does this actually control? In the literature, there is no understanding of what meanings representations like this can capture. For example, what information is perceived by listeners? Is the prosody more affect-related, or is it more related to discourse or information structure? This is important for the task of predicting appropriate renditions, since affect-related prosody may require information to do with mood or style of the speaker, whereas discourse structure prosody may be predictable from the history of the dialogue, and information structure may be predictable from standard linguistic features alone. In addition, we're also interested in the consistency of our representations across different contexts. The remainder of this talk will be split into two sections. First, I will talk about how we learn this discrete structure to control prosody, and then I'll talk about our experiments to determine what humans perceive in this learned structure. It is important to choose the correct prosodic domain when learning to represent prosody, since these representations can only capture a limited amount of information. In speech synthesis, representations are often learned at the sentence level. However, sentences are not prosodically relevant and can contain an arbitrary amount of prosodic information. Ideally, we would use prosodic phrase as our domain. However, phrase breaks are expensive to collect, and we did not have access to them for our data. There is also the question of how to choose prosodic phrasing when the audio is not available at synthesis time. We could use syntactic structure to get phrasing, however there is a mismatch between syntax and prosodic structure. In this case, we use a heuristic text-based parser called chinks and chunks. In this approach, there are two categories. Chinks are made up of function words and tensed verbs. Chunks are made up of content words and objective pronouns. These are used in a simple greedy regex, where as many chinks followed by as many chunks are matched. This is taking advantage of the right-branching nature of English, where content words, or objective pronouns, will cluster towards the right of phrases. I'll now describe how we learn our representations. I'll do so incrementally, slowly adding details slide by slide, beginning with this autoencoder. An autoencoder takes some input, in our case pitch, encodes it to some embedding space, and then decodes this to reconstruct pitch. Here you see that there are multiple embeddings in the embedding space, in this case 3. This is to represent that there are 3 phrases in this given sentence, and that we have an embedding for each of the phrases. The decoder takes, in this case, all 3 phrase embeddings, as well as the conditioning input of phones, and reconstructs the pitch. Instead, we use a variational autoencoder. The difference compared to an autoencoder is that a variational autoencoder models a distribution in the latent space, as opposed to a single point. And that is what you see with the normal distribution in the yellow boxes. Note that we have a different distribution for each phrase, and we sample Z tilde for each phrase and pass that to the decoder in order to reconstruct pitch. In addition, a variational autoencoder has a prior, which is what you see in purple. This prior enforces structure on the latent space. A vanilla variational autoencoder uses a unimodal prior, in this case a zero-mean unit variance Gaussian. This enforces a single mode in the latent space, and since we're trying to learn discrete or clustered structure, this may not make sense. Because of this, we use a different prior, a VAEVAMP prior, which stands for Variational Mixture of Posteriors. Put simply, this is a Gaussian mixture model. There are some complexities about how we learn the parameters of this model, but I will leave that for the paper. What is important to know is that because of this multimodal prior, our latent space can now have multimodal structure. The question then remains of how to do synthesis with this VAEVAMP prior model, since we do not have the green input pitch for the encoder. Since we have multimodal structure in the prior and the latent space, we can enforce discreteness by taking the mean of each component of the prior. While I haven't explained all the variables on this page, all that matters is that for each phrase, we choose the mean of one component as the point for that phrase. That can then be passed through the decoder to synthesize the pitch. Now I will talk about our experiments to determine how humans perceive our learned structure. For these experiments, we use children's audiobook data. This is 6.5 hours from a female speaker, and we use the Unilex phone set, meaning the input to our decoder is phone identity and 9 frame level features. For synthesis, we use the world vocoder. While this might not be as high quality as what we now expect in TTS, we're using natural smooth spectrograms and natural aperiodicity, so hopefully the quality is still decent. We're predicting interpolated log S0 as well as delta and delta-delta features, which are then smoothed using MLPG. In our listening tests, we used 12 different sentences, all with one phrase. We found quite interesting results for the sentence, "I'm sorry," and we'll discuss more about that later. First, I will play you 4 different renditions of this sentence from our proposed system.
I'm sorry. I'm sorry. I'm sorry. I'm sorry.
It's quite hard to get a view for all of the variation when comparing more than 2 samples at once. I'd encourage you to listen to more of these pairs offline by following the link in the description. In order to give you a more qualitative view of all of the variation produced by my system, this plot shows all 20 pitch contours for the sentence, "What's the matter now?" The top plot is for a baseline. This is a 2-stage approach. Please see the paper for more details. And the bottom is our system, VAEVAMP. For the top system, you see a lot of clustering around one central mode, with quite a wide range, but not different behaviors. On the bottom, we see a wide range, but over multiple different modes. At the beginning, we see 2 distinct modes. Towards the middle of the sentence, we see 3 distinct behaviors or 3 distinct modes. After this, we see some pitch contours shift between these modes, with 2 or 3 modes visible towards the end of the sentence. This is very nice behavior that is demonstrating what might be very distinct prosodic effects, and we will verify this through our listening test. Our first test looks at quantifying if the distinct behaviors seen in the plots correspond to perceived effects in the synthesized speech. As you heard earlier, it's quite hard to compare more than 2 samples without forgetting details. For this reason, we chose a forced choice preference test to determine if renditions were distinct. Users were presented with 2 renditions of one sentence for one system on each screen, and they were asked to decide if the two renditions have different intonation. Doing this test for all pairs of 20 renditions for two systems would be prohibitively expensive, so we chose 38 code pairs randomly for each system. 22 listeners participated in this test, and if we take the binomial significance test of these results, we find that both our baseline and our system were perceptually different, produced perceptually distinct renditions more than half the time, and our VAMP prior model was doing so significantly more than the baseline. Now that we know our system produces perceptually distinct renditions of a sentence, we want to ask the questions about what is perceived in these renditions. There are three aspects that we want to ask questions about. The first is on what kind of differences are perceived. Are they affective? Are they discourse structure related? Are they information structure related? The second is about their consistency. Do they behave the same across different sentences? And the third is about what non-experts perceive in this prosodic variation. We do not want to bias listeners' responses. As such, we perform qualitative interviews, taking free-form notes of the listeners' responses. On each page, listeners saw 12 sentences with 2 renditions per sentence, renditions coming from a particular code pair in the distinctiveness test. We used the top 6 code pairs to provide the strongest signal about how well this test works for determining interpretability, and we only used 5 listeners since this was a pilot test of a new kind. Here you see the exact notes taken during one of the interviews. We tried to record accurately what the listener said, and we asked for more detail when we weren't sure we were being accurate. Listeners weren't required to respond to every sentence and every rendition. They were free to respond to as many or few as they wanted. We took these free-form notes and tried to extract descriptive terms from what the listeners said. There was some level of interpretation happening here, but we tried to only write down a term where it did correspond to what they said, losing information where we could not convert to a term. From these lossy terms, we were able to verify that our model captures a broad variety of variation, with 68 total descriptive terms. The majority of the time, these were used to describe affect-related effects, such as upset and surprised. There were lots of other discourse structure-related terms, but these were not used as often. Interesting examples include insincerity, so insincere apology, fake impressed, or feigning surprise, as well as humorous sarcasm or typical sarcasm. We saw one example of information structure, where users described something akin to continuation rise. Looking towards the consistency of our codes, we found that some were reported as questioning, upset, and narrative quite regularly. However, these were the terms used most often in general. Overall, the interpretation of the codes changed depending on the sentence. We did find that the least descriptive sentences elicited more varied comments and more comments in general from listeners. These were sentences such as, "I'm sorry," or "What's the matter now?" These were sort of ambiguous sentences that could act as carriers for many kinds of prosody. In order to get clearer conclusions about this consistency, we would need more interviewees, since this was a sort of pilot test, and we might want to redesign sentences, maybe carefully accounting for how descriptive sentences are. Finally, we're interested in what non-experts focus on. Loudness and duration changes were reported by the listeners, though neither of these were modified. More interestingly, we found that interpretation reported by listeners seemed to be linked to imagination of some appropriate context. This didn't happen for all listeners, but some listeners would describe contexts in great detail. For example, for the sentence, "I'm sorry," one listener said, "When a kid says sorry but doesn't mean it," trying to get across a few different aspects of a context. This led us to an idea for a new prosodic perception study in TTS. Normally we only evaluate the overall goodness or quality or naturalness but instead we could have a test where users describe some context in which a rendition might be appropriate, allowing them to say unsure or invalid so as not to bias them. Analysis would be difficult, but by looking at descriptive terms or described contexts, we could determine if renditions consistently correspond to plausible contexts, uncommon contexts, or even the intended context were we to have that. To sum up, our discrete phrase-based approach was able to learn more distinct pitch contours, and users perceived mostly affect-related changes in prosody, as well as discourse structure and information structure changes of prosody. We would need more participants to make comments on consistency, and we would want to redesign sentences according to their information content. Interestingly, when hearing renditions, listeners would imagine and describe context which they thought would make these renditions appropriate, and this led us to suggest a new perception study for speech synthesis. Thank you very much for listening, and I hope you have a great virtual conference. The following links can be found in the description.